So, good evening, all. On the behalf of Department of Mathematics, Wilson College, Autonomous, Mumbai, I welcome you all in the today's session. So, our today's guest is Dr. Akshay Kumar, and he will deal with topic of multivariable calculus today. He has done his masters from IIT Madras. He has completed his PhD from MNIT Jaipur, and currently he is a postdoctoral researcher at the IIT Madras. So, more his area of interest is analysis, particularly functional analysis. Uh, on lighter note, one more achievement of him is he is a friend of mine. So, over to you, sir.
Thank you. Thank you for the introduction. So I hope I'm audible to everyone.
Yes, sir.
Okay. So let me share my screen. Is my screen visible to everyone?
Yes, sir.
Okay. So on day first, we have seen the limit of a two or three variable functions. In particular, we have seen epsilon delta form or and how to find a limit of a function, and we have also seen how to show that limit does not exist. So today let me start with this uh, question. Suppose you have this function x into e to the power x square plus y square upon y. So what can we say about the limit of this function at 0, 0? So take a few seconds and uh, observe the function. So last time we have seen that if you are able to find two different paths, suppose P1 and P2, and con- paths which contain the point where we are calculating limit, where we are determining the limit, and along these paths, if you have two different limits along path P1 and P2, if you get two different limit, then we say limit does not exist, right? So now what can we say about this function in this case? This is the question. So if you observe that now, suppose if you take path P1 as y equals to x, what is the limit of this function? So this function will be reduced as x into x square plus x square, right? Upon y is equals to x, so this is x. So there is no y, so we can write this function, this limit as tends to 0, right? So this will be limit x tends to 0 e to the power 2x square, right? So this will be 1. This is this is a question of one variable. I hope you all know this. Now, if you take the different path P2 as y equals to root x, so what can you say about this limit corresponding to this path? This will be limit. So this function now in this case will be reduced as x e to the power x square plus x upon root x, right? And there is no y, So we can write this limit as limit x tends to 0, right? And this is actually equals to limit x tends to 0 root x e to the power x square plus x. Now as x tends to 0, this part is going to, sorry, as x tends to 0, this part is going to 0, and as x tends to 0, this part is going to 1. So in total, this limit will be 0. So what can we say about this limit? So this does not exist. So in the end of the last session, we were doing this type of questions, right? So let me put one more question here. So now suppose you want to calculate this type of limit. F is a function from R2 to R, right? And I'm also calculating limit y. So this is A, this is B. Y tends to B, limit x tends to A, f of xy. So what can we say about these two limits? Have you seen these limits?
Yes, sir.
So these, if I'm not wrong, these limits called simultaneous limit, right? So in general, these limits are not equal. So I can give you an example. If you take this example, x square plus y square upon x square, x plus y square, where the denominator is not equals to 0, right? Take this function. Now calculate the first part. Uh, limit x tends to 0, limit y tends to 0 of fxy. So what is this limit? What is the value of this part?
Zero.
Okay, someone is saying 0. Okay, so this is, so see this part. Treat x as a constant. So this will be limit x tends to 0. Now we are solving this part, limit y tends to 0, x square plus y square upon x plus y square, right? So this will be, now y is going to 0. So this part will be 0. So that means this is limit x tends to 0. So numerator will goes to x square, right? Because y is going to 0. And the denominator part will goes to x, right? So in total, the function will be equals to x. And now x is going to 0, so this part will be equals to 0. Now similarly, if you calculate the right hand part, so what's the value of this part? Try to answer this part. So this is x square plus y square upon x plus y square, right? Now x is going to 0. That means the numerator part is going towards x square. So x is going to 0, so this will be y square. Now the in denominator part, x plus y square, x is going to 0, so this will goes to y square. So what is the limit of this part?
1.
So this is 1, right? So these limits are in general not equal. So these limits in general are not equal, right? Now, now I can ask one more general question. So suppose I'm giving you s is a function from R2 to R, right? Now I'm giving you that suppose limit x tends to a, limit y tends to b, f of xy is equals to limit y tends to b, limit x tends to a of fxy. I'm giving you that both the limits are equal. So what can we say about, and I'm saying this is actually equals to L. So can we say limit xy tends to a comma b of fxy is equals to L? Can we
No,
say this? Someone was saying something.
no, sir.
Yeah, right. So we cannot say anything about this. Right. So I can give you one example for this one. So you take fxy is equals to xy upon x square plus y square, right? So you can check that this limit x tends to 0, limit y tends to 0 of this function is actually 0, right? And similarly, okay, so, oh yeah, right. And this is actually equals to limit y tends to 0, limit x tends to 0 of fxy. So both limit exist and equals to 0. But limit xy tends to 0, 0 of f does not exist. You can check this part. I'm not going into this now. So let me ask you one more question. So what can you say about this limit? So what can you say about this limit? Function is sine under root x square plus y square upon under root x square plus y square. So what can you say about this limit?
1,
Why?
sir, because it is sin star upon star type where star tends to 0.
Oh, that is in one variable. So you are saying, so your idea is correct. So reduce this function in one variable. So idea is reduce this type of function to one variable problem. So and the best way to reduce two variable problem into one variable is the polar form. So what is a polar form? Suppose this is your R2, right? So suppose here is your point x comma y, and this is your origin, right? So and we say this is your distance r. R is the distance of this point xy from origin. So this will be under root x square plus y square, right? And suppose this angle is theta, right? So you can check that this distance, this length, value will be r cos theta, and this is actually equals to x, right? Similarly, you can check that this value is actually equals to r sin theta, and which is equals to y, right? So x is equals to r cos theta, y is equals to r sin theta, right? And r equals to under root x square plus y square, right? Now suppose x goes to a and y goes to b, then this will imply r goes to under root a square plus b square, right? So our question was, so limit x y tends to 0 0, right? And sine under root x square plus y square upon under root x square plus y square, right? Now use polar form. So this will reduce to limit. Right? Let's see the function sine under root x square plus y square. So we can write this is as sine r upon, this is again r. Now there is no theta. And since x y goes to 0 0, so r will goes to 0. Right? Now this is one variable problem, and this will be equals to 1. Right? So now in this way you can solve. In this way you can reduce two variable problem into one variable. And similarly you can solve this part x y tends to 0 0, say cos x square plus y square upon x square plus y square. Similarly you can do this part also, right? So let's move to continuous function. Just a second. Now move to continuous function. So suppose recall that, now suppose you have function of one variable, right? How you define continuous function there? So f is said to be continuous at a point, say a, if limit x tends to a, f of x exists, and this limit x tends to a, f of x is actually achieving by the function. So this is also true. If this is true, then we say that the function is continuous at that point. And if f is continuous at every point of domain, then we say the given function is continuous everywhere. F is continuous everywhere. F is continuous simply. Right. So similarly, if you have function in two variable, right? So we say this function is continuous at a point a comma b if limit xy tends to a comma b, f of xy exists and also equals to a comma b, right? So this type of function called continuous function, right? So you can observe here to determine limit of a function. Determine limit of a function, say f, no matter what your domain is. So let me, this is your function, say a to r, right? Determine limit of function f from a to r at point a. So then this point, at the point a, the point a may not be in the domain. So actually what I'm saying is, so to determine limit of a function at some point, so that point may not be in the domain. We don't need that point in the domain, right? Still we can calculate limit because we are just calculating where this function is going, where is this function is approaching, right? So that point may not belong to the domain. But if for the continuity, we need that point in the domain, right? And one easy example is all polynomials are continuous functions. Continuous, right? Okay. So now let's solve some question which have come in previous year. So let's okay. So okay. In 2019, right? This is the question. So in 2019, so probably this exam was conducted by IIT Madras. So they have asked, suppose you have this function. No. Okay. So suppose you have this function, right? F of x y equals to x square mod x to the power beta y upon x to the power 4 plus y square when x is not equals to 0 and is 0 if x equals to 0. Now check at the point origin the function is. So now the first option is continuous at b for b equals to 0, beta equals to 0, continuous for beta greater than 0. Let's check all these options. So now for beta equals to 0, so for beta equals to 0, this function f of xy will be equals to x square y on x to the power 4 plus y square, right? And 0, right? This is x not equals to 0, x equals to 0. So what can you say about the continuity of this point? So now first check limit of this function. Limit xy tends to 0, 0. Function is x square y upon x to the power 4 upon y square, right? Now take this path, y is equals to mx square, right? So this function will be reduced to limit xy tends to 0, 0, and this is equals to x square and y equals to mx square. So m x square upon x to the power 4 plus y square. So m square x to the power 4, right? So this is actually equals to limit xy tends to 0, 0, right? So this, in numerator we have x to the power 4, and denominator also we have x to the power 4, x to the power 4. So in total we will have m upon 1 plus m square. So no x and y is in the function. So this will be equals to m upon 1 plus m square, right? So now if you take m equals to 1, then for that path limit will be 1 upon 1 plus 1. For m equals to 0, you will have value will be 0, right? For m equals to say minus 1, you will have minus 1 upon 1 plus 1. So you are getting different limit along different paths. So what can you say in this case? Limit xy tends to 0, 0 of this function of fxy does not exist. Okay, are you following me?
Yes, sir.
Okay, so the first option is not true, right? So now let's check the second option, B option. So the for b greater than 0, so the function is, so now our function will be f of xy is equals to x square mod x to the power beta y upon x to the power 4 plus y square x not equals to 0 and 0 if x equals to 0. Now we want to check limit beta is greater than 0, and we want to check limit xy tends to 0 comma 0 of this function, right? So better way is to write this function in this way. X square y mod x to the power beta. I'm just rearranging the terms. Nothing else I'm doing. So now, what can you say about this function? What can you say about this limit? Try to, try to solve this part. If you remember, last time I told you when inequality. So for A and B, real number, you can take it both are non-zero. So then mod AB is always less than equals to A square by 2 plus B square by 2. Right? Now, now see this part. Now, now see this part. So suppose this is your Z and this part is your F. Right? So now you can observe that limit x tends to 0 mod x to the power beta is equals to 0 because beta is greater than 0. Right? Now, if I can prove that this is a bounded function, then in total, what I will have? I will have that xy tends to 0, 0, f into z. So f is already given there, so I can assume this h. So in total, what we'll have? Z into h. This is equals to 0. Remember this property?
Yes,
Okay. So now take a equals to x square and b equals to y square. Right. So what will you have? Y only. So x square y mod is less than equals to x to the power 4 by 2 plus y square by 2. Right. So what will you have in left hand side? X to the power 4 plus y square mod. This is less than equals to 1 by 2. So this is your function z, right? This is your bounded function, right? And you are saying z is bounded and limit xy tends to 0, 0 of function x is 0, right? So in total, what will you have? Limit xy tends to 0, 0, z into h. This is equals to 0. And this is exactly your function limit xy tends to 0, 0. This is your function f, given function f. So limit at 0, 0 is 0. Now, what's the value of f 0, 0? So you in the question it is given that if x is 0, then your value is 0. So in 0, 0 point, x is 0. So this is also 0. So limit is actually attending that by the function. So this function is continuous for beta greater than 0. This option is true, right? Differentiability we will discuss later. So let's try D part. What will happen if beta is less than 0, right? So suppose your function is, no, suppose beta is less than 0, right? And your function is, again, your function is fx square, x square mod x to the power beta y upon x to the power 4 plus y square, where x not equals to 0, right? It is given in the question. Okay. So now you want to try this part, right? So we are checking for beta less than 0. So for particular, I can check for beta equals to -1, right? Even you can check for beta equals to -2. So then for beta equals to -2, the function will be equals to x square. This will be x to the power -2, y upon x to the power 4 plus y square, right? This will be equals to y upon x to the power 4 upon y square, right? Now, if you take y path equals y equals to x square, then your limit x y tends to so see this function will be reduced to x square upon x to the power 4 plus x to the power 4, right? X tends to 0 because y is there is no y in the resulting function. So this will be equal to limit x tends to 0, 1 upon x square. So this is actually going towards infinity. So this function cannot be continuous at 0, 0 for beta less than 0. For beta equals to -2. In particular, you can do this part for any beta less than 0. So this option is also not true, right? So the only option, it's actually a single option type question. So the only option correct is B. A, we have seen A is not true. We have seen D is not true. Once we discuss the differentiability of these functions, you can check this function. This is also not true, right? So are you following me?
Yes,
So have you understood the question and the solution of this question?
yes, sir.
Yes, sir.
Okay. So let's try some other question. Okay. This question arrived to 2019. No, we can solve some question. One question was there. Okay, this is the question. Okay, this is the question. So suppose Suppose B is a subset of R square. Okay, and this subset is of this form. Okay, first takes a few seconds, read the question, understand the question, then give it a try. This is the procedure to solve a question. So suppose your set is, so this is your R square. Now you delete your x-axis. This is your domain, right? Now, what is your question? What is your function? Fxy equals to x into sine 1 upon y. Now, observe that. Suppose you have this function g of x equals to 1 upon x not equals to 0. So, where this function is continuous? This is a one variable question, one variable function. So, where this function is continuous?
Open 0, infinity,
Open 0,
infinity.
I'm saying this, suppose this is a function from r minus 0 to r, and I'm saying g of x equals to x. So I'm asking where this function is continuous. So this will be continuous on whole domain r minus 0, right? Only the problem point is 1 upon x. So this is this type of function. On 0, limit does not exist, but other than 0, this function is continuous everywhere, right?
Yes.
Okay. So now I can ask you this. Suppose this is your function fx equals, so say hx equals to sine x. So where this function is continuous.
Everywhere.
So yeah, this is continuous everywhere on R, right? So now I'm saying this, take this composition sine 1 upon x. So now I'm asking where, so f is already there. So now take this is x equals to this sine x. So f g h. So say you can take k. H is this. So I'm asking now where this function is continuous. So you can write this function as h composition with your g function, right? You can write this function, right? Because gx is your 1 by x and hx is your sine x, right?
Yes, sir.
Okay. So that means this function is continuous
At r minus
except
0.
except r except 0 only. Continuous on r except 0. Okay. So now in particular, what I can say is, so this part is continuous, right? If y is not equal to 0. And the first one part is always continuous because it's a polynomial. Product of two continuous functions is always continuous. So the in total the product is always continuous, is continuous for y not equals to 0, right? But y equals to 0. So let me, yeah. So y equals to 0. This is not domain, right? In question, they have mentioned that your domain is r square minus this point. So the only points where y is 0 is the x-axis, right? And that's not in your domain. So you can say this function is continuous everywhere in the domain, right? Are you getting my point?
Yes, sir.
Yes.
So this function is continuous. So the function x into sine 1 upon y is continuous on r square minus x axis, right? And this is our domain D. So this is continuous in our domain. Right. So let's see first option. So the first option is saying f is discontinuous on f is a discontinuous function on D. So that's not correct. We just have seen that f is continuous in our domain, right? Are you following me?
Yes, sir.
Okay. So let's see second part. So I can erase this part. So first read the second part, second option. Then we will give it a try. So the second option is saying f is continuous function on D. That is true. This part is true, right? And it is also saying that this function cannot be extended continuously to any point outside the domain D. So you first calculate limit xy tends to 0, 0 of this function. So I can directly write the function. So the function is x into sine 1 by y, right? So if you observe that, again you can use that this function is a bounded function, right? This function is going to 0. So in total limit will be
0.
0, right? Now, if I define this function as fxy is equals to x sine 1 by y, if x not equals to x and y both are not equals to 0, and if and 0 if xy is equals to 0, then this function is continuous at 0, 0, right? Because
Yes.
limit is 0. So I can extend this function continuously to at 0, 0, 0. But the second part is saying cannot be extended continuously to any point. But I can extend this function continuously at 0, 0. So this part is not true. So this option is also not true, right? Now we have just proved that f is continuous. This is true. Now, can be extended continuously to D union 0, 0. On D it is continuous. Already we have proved. And on 0, 0 we can extend this function as a continuous function. This is also true. So this option is true. Right. So now the last option is saying that f is a continuous function. This is true. Now, can be extended continuously to the whole R square. So the option D is saying you can there is nothing special in 0, 0. You can extend this function continuously to any point of R square. So let's check that part. So now you take any point. So I can take this point 1 comma 0. This is not in D, right? D is R square minus x axis. So this is a point on x axis. So let me check. Let's check. This can we extend this function continuously to this point. So suppose you can extend this function continuously to this point. So then limit xy tends to 1 comma 0 f of xy must exist. Otherwise you cannot extend, right? So let's say the limit of this part. So the your function is x into sine 1 by y. Right. Now, if you take this part, y is equals to uh, okay, 1 plus x, or you can just simply take, you take this part, x equals to simply 1. So this part, x equals to 1, this line contain this point, right? Now, if you put x equals to 1, then limit sine 1 by y and y tends to 0 does not exist, right? So if limit is does not exist, you cannot extend that function continuously to that point. So you cannot extend this function continuously to this point. So this is not true. Even you can prove that except 0, 0, you cannot extend this function continuously. If your point is, suppose your point A comma B, you have take, if you take this point and your A is non-zero, B is also non-zero, and this does not belongs to your domain, then you cannot extend this function continuously to this point. You can prove this also. So in total, this part is also not true. So the correct option is C. Right? Understood?
Yes, sir.
Okay. So now we can try more question. Okay. Yeah, this is the question. So in 2023, they asked that suppose you have this function x square minus 1 to the square cos square y square upon x square minus 1 to the square, right? For x not equals to plus minus 1. And if x equals to plus minus 1, then your function is 0. Now they have asked for how many points the function is discontinuous, right? So your function is x square minus 1 to the square. This actually this function looks weird, but it is easy to calculate. Cos square, then y square upon x square minus 1 to the square. If x is not equals to plus minus 1 and is 0 if x equals to plus minus 1. So this is your function. So suppose now first check when x equals not equals to plus minus 1, right? So now, so this function x square minus 1 to the square, what can you say about this function when this function is continuous?
Yes, sir. It's continuous.
When, so this is continuous for
Everywhere.
all x not equals to plus
Plus
minus 1.
minus one.
Yeah, you are saying because this is not in our domain, so you can say this is continuous everywhere, right? So again, so where this function is continuous, so say hy equals to y square. This is continuous everywhere,
Yes, sir.
okay? So in total, you can say y square upon x square minus 1 to the square. This is continuous for all x not equals to plus minus 1.
Yes, sir.
Right? Because denominator is also continuous, numerator is also continuous. Right? Now the next one is cos square. So this function, so say k of x. This is cos square, so z and z. Cos square z. Where this function is continuous, this is continuous everywhere.
Yes, sir.
Right? So in total by composition of these functions, you can say cos square y square upon x square minus 1 to the square. This is continuous for all x not equals to plus minus 1. Right?
Yes, sir.
Now remaining is this part x square minus 1 to the square. This is a polynomial. This is continuous everywhere. So in total, you can add x square minus 1 to the square into this part. Also here, this is continuous for all x not equals to plus minus 1. Right? The
Yes,
only
sir.
points we need to check is to take any, so plus minus 1 and y. So only points remaining are, so this is your, so this is x, so this line and this line. So here x equals to 1, here x equals to minus 2. So these points are actually remaining. Now, if you check limit x, y, so say y naught is any particular point. You can take, suppose this is any particular point either on this line L1 or this is in on line L2. So if you map plus minus 1 y naught, if xy tends to plus minus either plus 1 or minus 1, you can take any one. If you take this limit f of xy, right? So now see, your function is this function, right? And your function is this function. So if you see, this is your f. If you take this f and this is your z, this is a bounded function,
Yes, sir.
right?
Yes, sir.
This is a bounded function. And if you x map to plus 1 or minus 1, whichever point you choose, f goes to 0, right? If
Yes.
x maps to 1, then this part goes to 0. If
Zero.
x goes to minus 1, then also this part goes to 0, right? And it's actually independent of y. Whatever y you choose, it's independent of y, right?
Yes.
So what can you write here is, so if whatever y naught you choose, if xy maps to plus 1 y naught or minus 1 y naught, then this limit will be equal to 0 only, right? And what is the value of this plus minus 1 y naught? What is the value when x is plus 1 or minus 1? And in the
Zero.
function given, if x equals to plus 1 or minus 1, then value will be 0. So this function is continuous everywhere. So how at how many points this function is discontinuous?
Zero.
So this function is, yeah, right. This is function is continuous everywhere, continuous on R square, right? So there is no point where this function is continuous. So the answer is 0, right? So in this way, you can solve these type of questions. These questions looks weird, but these questions are actually easy to handle. You can handle these questions very easily. Just break these the weird part into smaller parts. Then you can solve this part easily. Okay. So now let's move to some other topic. Okay. So now let's move to partial derivatives. Okay. So recall that suppose you have a function from R to R, right? So if you have any point, as I mentioned in the last class, last session, so if you have any point here, A in the on R, so there are only two ways to approach this point. So one is from left hand side, and another one is from right hand side, right? So in that in that case, you have defined that f dash at any point x naught is actually equals to limit s tends to 0. You can take okay. So this is f of, I made some space here. So this is actually equals to limit x tends to 0 f of x naught plus h minus f of x naught upon h, right? Now, here in R square, you have too many directions, right? Now, if you suppose your point is this one, right? Or you can suppose the point is this one, right? So if you approach this point along this axis from this direction, then this called partial derivative with respect to x. If you approach this point from this line, then it's called partial derivative with respect to y. And these will be denoted by, along this line, it will be denoted by del f upon del x. And along this line, it will be denoted by del f upon del y, right? So we will see these, we will see proper definition of these derivatives. But one may ask, so what's special in this direction? I can approach these points from many directions. So yes, you can approach this point from different directions, and you can calculate derivatives along that direction, and probably that called directional derivatives, right? So uh, probably we are not going into that. So the actual definition for this is the limit. So see, in this line, the y is fixed, right? The second variable is fixed. So limit s tends to 0. So if suppose I am calculating as xy equals to x naught into x naught and y naught. So this will be equals to f of x naught plus h. Y naught will be fixed minus f of x naught y naught upon h. Right. Similarly, you can calculate this along this line. This line x is fixed, right? So at point xy equals to x naught y naught. So this will be equal to limit. So you can say k, but I am again writing h as tends to 0. F of x naught is fixed. Now we are working on the second tuple. So minus f of x naught y naught upon h. Right. So this will be your partial derivative with respect to x and y. Similarly, you can do for z also. If you have third tuple in your function, there is nothing different in that case. Right. So now suppose I can give you one function. Suppose f(x, y) equals to. So suppose this is your function x square upon x square plus y square when x y not equals to 0 0 and 0 if x y equals to 0. Now find the partial derivative at point 0 0 and del f upon del y at point 0 0. Try to calculate these derivatives. Are you trying this part or?
Sir, del f by del x doesn't exist and del f by del y is 0.
Okay. So this will be limit s tends to 0 f. So we are calculating at 0, 0. So this will be 0 plus h. Y will be fixed minus f 0, 0 upon h. So if you plug this point 0 plus h, so this is h comma 0 in the function. So we are taking h not equals to 0, of course. So then this will be h square upon h square and y 0 minus 0 upon h and limit s tends to 0, right? So this will be equals to limit s tends to 0, 1 upon h, and this limit does not exist, right? So that means this derivative does not exist, right? Similarly, if you try for the del f upon del y at 0, 0, then this will be limit s tends to 0, f of first variable will be fixed 0 plus h minus f of 0, 0 upon h. Okay, so this will be, now plug this point in the function. So this will be so x is 0, so this part will be 0, so this is 0 minus 0 upon h, limit s tends to 0, this will be 0, right? So in this way you can calculate partial derivatives. Now I'm interested in this question. So suppose f is your function from R to R, right? And I'm saying this is your point A in R. And I'm saying suppose if this function is differentiable at this point A. So in general this imply f will be continuous at A. Probably you all know this. This is true in one variable, right? Now I'm saying suppose you have this function f from R2 to R, right? And I'm saying a comma b is any point in R square, and I'm saying both partial derivatives at comma a comma b and at comma b exist, means you can calculate this part. So is this imply that f is continuous at 0 a comma b? So this is my question. Can you say this? Suppose both the partial derivative at point a comma b exist. Can you say f is continuous at a comma b?
Yes.
So someone is saying yes. Okay, let me give you one function. So let's take this function x square plus y square upon x square minus y square. This is when x not
No,
equals to
sir.
y. Okay, and I'm
No, sir.
saying
सर
yeah,
ऐसा हम नहीं कह सकते कि फंक्शन कंटिन्यूअस होगा अगर ये एग्जिस्ट करे तो भी.
yeah, we cannot say. I'm coming to that part only. This is 0 if x equals to y square, right? Now for this function calculate this part. at 0, 0, and also calculate this part. Even if you can simplify this question as you just take minus in the upper part plus in the lower part, and you this is xy not equals to 0, 0, and if xy equals to 0, 0. You try this part. So in the first part, what we are saying, so calculate this limit s tends to 0, f 0 plus h comma 0 minus f of 0 comma 0 upon h. Right? This is equals to this one. So this will be equals to f 0 plus h comma 0. So this will be h square minus 0 upon h square plus 0 minus 0 upon h. Right? Okay. So in this case, limit. Okay, in this case, derivative is not exist. Okay. Okay, what will happen if I replace this part by
Sir, XY.
x? Right. So then this part will be 0. This will be 0. Right. Similarly, you can prove that this is also 0. And of course, and you can also prove that limit x comma y tends to 0, 0 xy upon x square plus y square does not exist. Even you were asking for, means we were asking for something more, continuity. Even this function is saying both partial derivative are exist. Still, limit is limit does not exist at that point. Even you can't guarantee limit at that point. Continuity is little bit far from that, right? But actually this is for roughness of this function. This function is very rough, right? Roughness. But if the function is not that much rough, then you can guarantee that this will be true. Even this is true if both the derivative exist and continuous at that point. If you have continuity of these parts, then you can guarantee that this will be continuous. But in general, if the function is rough, that means may not be continuous. These derivative may not be continuous. Then f may not be continuous. Even limit may not be exist. Right. So even I can say here, you can say that if del f upon del x at point say a comma b, and del f upon del y at comma a comma b exist and continuous, then f will be continuous at a comma b. Right. Now, so till now we have calculated one derivative, del f upon del x, del f upon del y. Even we can calculate del upon del y and del upon del x. So this is called del x del y. Okay. Oh, sorry. So now we are operating y first. That will be del y del x of l. Yeah. This is say this one, and this is say del upon del x del y. Right. So note here that in general del f upon del y del x not equals to del f upon del x del y. In general, it's not true. Right. So when they will be true, when this will be true, when they will coincide, if this is called accelerate form, accelerate theorem. If both, so this can be written as f y x, and you can write this as f x y. Right. You can write this as f x. You can write this as f y. Right. So if both f x y and f y x exist and continuous at a comma b, then fxy at point a comma b will be equals to fyx at point a comma b. Right. In general, they are not equal, but if you have some condition, then they will coincide. Right. Now we can solve some questions of partial derivatives. So in 2023, they have asked this question. Okay, so this is also of our scope. So 37. So in that question, they have given this function, right? So first option is calculate this limit, right? Now, if you put t and t, if you plug this point, t tends to 0. So we can take t not equals to 0. So this will be equals to, so if you solve this part, so this will be t to the power 4, t to the power 3 minus 0. This one is t to the power 6 plus t to the power 6, okay, and minus 0 upon t, and limit t tends to 0, right? This will be equals to limit t tends to 0, t to the power 7 upon, this is 1 and 2, so the 2, t to the power 6, and t is also there, t to the power 7. This equals to 1 by 2, right? So this option is true. Right. Now try the D option. Try for this part.
Not
And
true, sir.
okay, you are saying not true.
Hmm.
Anyone else is trying? Any other person is trying? No one is responding other than. So okay, let's calculate this part. So this will be limit t tends to 0 and put plug t at the place of x and 2t at the place of y, right? So this will be t to the power 4, 2t to the power 3 upon t to the power 6 plus 2t to the power 6 upon minus 0 upon t, right?
Yes, sir.
Okay. So many persons in comment box are saying false. Okay. So this will be equals to, so this is 2 to the power 3, t to the power 7 upon, this will be 1 plus 2 to the power 6, t to the power 6 in 7, limit t tends to 0. So this will be equals to 2 to the power 3 upon 1 plus 2 to the power 6. So this is not exactly not, this is obviously not equal to 1 by 3. So this is not right.
Yes, sir.
Okay, now try B option.
It's 0.
Okay, you are
Both,
saying this is true.
both partial derivatives equal exist and equal to 0.
Yeah. So for this part, just a second, let me see the. Okay. So let's calculate this part. So limit x tends to 0, f of 0 plus h, comma 0 minus f of 0, comma 0 upon h, right? So if you put y equals to 0, so then this part will be 0. This is 0 given, so this will be 0. This is true. Now similarly, if you solve this part, limit s tends to 0, f of 0, comma 0 plus h minus f of 0, comma 0 upon h. So if you put x equals to 0 in the function, so the function will be 0. So this is 0, this is 0 given, this will be 0. This is also. So correct options are A, B, and C. Right. Now let's see some other questions in this paper. 2023. So okay, you can try this part. So your function is this one, fxy equals to ln 1 plus x square plus y square. So so this function is actually continuous and partial derivative always exists. So you can directly calculate these partial derivatives and try to find which option is correct. So there is no need to check whether the partial derivative exists or not. Simply calculate. If you are calculating del f upon del x, you just calculate df upon dx and treat y as a constant. Treat y as a constant. You can do that. So first calculate t. So del f upon del x will be 1 upon 1 plus x square plus y square, right? And by chain rule, this will be 2x, right? You know chain rule, right?
Yes, sir. Yes, sir. Option B is true here.
Okay, let's see. So this is 2x. Now calculate del square f upon del x square. So this will be equals to, so 2, 1 plus x square plus y square minus 2x. This will be 2x upon 1 plus x square. So this will be whole square. No, x plus y square to the whole square. Now if you put xy equals to 0, then you will get 2. Okay, this is true. Similarly, you can check this will be also, this is actually equals to 2. And you can check this one is 0. And even this one is also 0. Right? So this is your P. This is your P. Right? This is your S. This is your Q. This is your R. Right? So P is greater than these two. So this is greater than 0. This option is not true. This option is not true. Right? So P is greater than 0. P is greater than 0. Right? So now P into S will be 4 and Q into R will be 0. So PS minus QR will be 4. So will be greater than 0. This minus 4 is greater than 0. So the option B is correct. Right?
Yes, sir.
Okay. Okay, you can try this one also. Suppose you have this function e to the power x square plus y square, and a, the sequence an is the determinant of this matrix at the point, this point. So what is the limit of this? Try this part.
Option D.
Option D. Okay. You have the answer key or you are trying?
No, sir.
You are actually trying.
Yes, sir.
Okay. So let's try this part. So if you find del f upon del x, so this will be equals to e to the power x square plus y square into 2x, right? And if you calculate del square f upon del x square, so by product rule, this will be equals to 2 e to the power x square plus y square plus 2x into 2x e to the power x square plus y square, right? So this will be equals to 2 e to the power x square plus y square plus 4x square e to the power x square plus y square, right? Now, if you check your point x and y, x is this and y this. So if you observe that x plus y square, what is the value of x square plus y square? So your x is cos n, right? Y is your sin n, right? So this will be equals to cos square n plus sin square n. What is the value of this?
1.
1, right? So if you simplify this term, so this will be 2e plus 4. Let's keep x as it is. So this will be e, right? Now similarly, if you calculate del f upon del y, so this will be equals to 2y e to the power x square plus y square. And if you calculate the double derivative, so this will be 2 e to the power x square plus y square plus, okay, so we have missed something. No, okay. So this will be 2y to the square e to the power x square plus y square. This will be equals to 2e plus 4y square, right? So one term is this, one term is this. Okay. Now calculate. Now calculate del square f upon del x del y. So this will be equals to, so you can use this part. So this will be 2 e to the power x square plus y square into 2x, right? Plus, so this will be, this is 4y square e to the power x square plus y square. This is will be 8y square, 8y e to the power x square plus y square, plus you will have okay, this is 4y square and 2y e to the power x square plus y square. Are we doing something wrong?
सर इससे थोड़ी ना, इससे ऊपर वाले का करो, डेल एफ बाई डेल वाई।
Okay, this part.
आपने
Okay,
आपने
okay, okay,
डेल
okay. Okay, okay, sorry. That's why I thought we are doing something wrong. Okay, use this part. So this will be equals to 2 e to the power x square plus y square, plus this will be 2y to the square e to the power. Okay, so
सर
we are
टू
going with respect
टू
to
एक्स।
x. Respect to x, so this will be 4xy e to the power x square plus y square, right? This will be 2 plus 4xy e
टू ई।
and e. Okay, now this is correct. Okay, and since these functions are continuous, so by quadratic theorem, this will be equals to del square f upon del y del x.
यस सर।
Okay, so our matrix An will be determinant of, so first part is 2e plus 4x square e, right? Second term is 2e
ई
plus
और
4xy
एक्स
e,
वाई।
right? So the same term is there for xy e, and here again we have 2e plus 4y square e, right? If you solve this part, this will be equals to 12e square, I think. Okay, and you have asked to calculate limit n tends to infinity an. So this is a constant sequence, so this will be equals to 12e square. So it's a small calculation, you can calculate this part, and in between you can use x square plus y square equals to 1, right? So this final answer will be this one, right? So now we can, okay, okay, let's do this question. Okay, this question. In 2019, they asked that suppose your function is this. Now, which one is correct at 0, 0? Now, take a few seconds, and read the question, understand the question, then read the options, then try the question. This is the procedure. Right, your function is this one, right? And you have asked to ask which one is true for true at 0, 0, right? Now, first option is whether f is continuous at 0, 0 or not. So let's try that part. Okay. So if you observe that, so if you can split this function in two parts. This is your first part. So say this part is g, and this part is your f. Right. Now this is uh, now if x goes to 0 0, now limit x y goes to 0 0 of f. F is your under root x square plus y square. This is 0. Right. So this part is going to 0. Now whether g is your bounded function or not, your function g, what is g? Your g is mod x upon mod x plus mod y. This is a bounded function or not?
Yes, sir.
Why? Give me a bound. Why this function is bounded? You are taking this much time. So you see, this mod x is always less than equals to mod x plus mod y, right? And you can see from here that this one mod x and this is your 0, greater than 0, right? So mod x mod y to the, and this is a positive function. This function
Sir.
is always less than equals to 1,
Yes, sir.
right? So this is your bounded function, right? So what is the limit of this function now? Okay, I should have written this is your function. F is already given in the question, so I should write the h, right? So in conclusion, what you can write is limit of fxy will be, what is the limit of this function?
0.
0. And what is the value of f00?
0.
0. So so can you say a is true?
Yes, sir.
Okay, so a is true. Right. Now try second one. So all three are related to partial derivatives. So just calculate partial derivative at 0 0. Some people are answering in the chat box that this is less than equals to 1. Yeah, you are right. This is a bounded function. This function is always less than equals to 1.
Uh, Both are equal to 0, 0.
Okay, that's right. So first we need to calculate del f on del x at 0 0. So this will be equal to limit s tends to 0, right? F of 0 plus h comma 0 minus f of 0 comma 0 upon h, right? So now if you put these values, this will be equal to limit, so mod 0 plus h. So this is mod h and upon mod h y 0 under root x is h to the power 4, right? And y 0. So this will be equal to limit x tends to 0. So this part will be cancelled out. So this limit is going to 0. So this is actually equals to 0. right? So this part is true. Now, similarly, if you calculate del f on del y, this will be equal to limit as tends to 0, f of 0, comma 0 plus h minus f of 0, comma 0 upon h, right? So if you plug in the values, so this will be limit as to 0. So x is 0. This is 0 into something. So this will be 0 minus 0 because x is 0, right? X into something, x is 0 and 0 into something is always 0. So this is h. So this will be 0. This is also true. So our correct options are A and D, right? If you have any doubt, any question, you can ask me. Okay. So let's try some other questions. So okay. Okay. Try this part. So it is given that g is a function from R to R, which is a twice differentiable function, and your f is gy plus x g dash y, and you have asked to ask for the correct option. So your function is f of x y is equals to zy plus x dash y. Are you trying for this?
Yes, sir.
Okay.
Option C is correct.
Okay, someone is saying option C. I don't know. I also have to calculate.
C is correct, sir.
Okay, 2% are saying C is correct. So let's try. So we need to calculate. So see, in all the options del f upon del x is available, del f upon del y is also available, and del 2f upon del x del y is also available. Right. So let's calculate this part. So first calculate del f upon del x. Right. So this is actually equals to. So now this function is this is a function of y. Right. We are calculating partial derivative with respect to x. So treat this function as a constant function. So derivative of this part will be 0. Right. Plus, and this is a constant for this in this case. So this will be z dash y only. Okay, what's person are saying? Okay. Now similarly, if you calculate del f upon del y, so this will be z dash y because this is a function of y plus x will be same z double dash y. Right. Right. Now if you calculate del f del square del x del y, so this will be, so now you are calculating with respect to x. So this is actually equals to del upon del x, del f upon del y, this part. So the first part is function of y, so this will be 0 plus the second part. So this will be z double dash y. This is actually z double dash y, right? So if you observe that, if you add this quantity and this quantity, and if you multiply this part with x, right? So add this part and you will get this part, right? So in total the answer will be del f upon del x plus x del square f upon del x del y. This will be equals to del f upon del y. So this will be our answer. So in C part del f upon del x, so del f upon del x, so plus x upon del square f upon del x del y, this part, and this is equals to del f upon del y. So the C part is correct. Right? Okay, many questions are saying. Okay. Now we can move to some. So let me check whether I have some other question or not. So this is 2020. Okay. Okay. Now we can move to some other topic. So now we can move to the application of these derivatives or these what we have done till now. So recall. So in particular, I will talk about maxima and minima. Right. Now, suppose you have a function from r square to r. Right. So when you say a b, so I'm talking about local maxima or relative. You can say relative maxima and minima. So we say this point is a local maxima point if the function given function f of a comma b is less than equals to f of x comma y for all x y belongs to u. U is some neighborhood of the point a comma b, right? Or you can say in neighborhood means you can take circle, some circle containing this point a comma b, right? Or you can say you can also take this square also. There is no difference between these two objects, right? And similarly, this point is called a local. Okay, this is local minima, and this is a local maxima, maximum point if this function f from a comma b is less than is greater than equals to f of x comma y for all x y belongs to u. Again, u is some neighborhood of a for this is not every neighborhood of u, not neighborhood of a comma b. This is some neighborhood of a comma b, right? This is some, right? So in particular, so I can ask you this thing. Suppose you have function from R to R, right? So what's your critical point? How you define critical point in one variable case? Suppose A is a point in R, right? When you say this point is a critical point, am I audible to everyone?
When its derivative is zero or does not exist.
So yeah, right. So if the first point is the derivative at this point, f dash a exists and equals to 0, right? And the second point is f dash a does not exist, right? And there is a very famous theorem in one variable case. Suppose f is a function from R to R and a is any point in R where f attains its local maximum or minimum, then a has to be a critical point. So if you are checking for local maxima and minima, so just check for critical points only, right? So there you will have local maxima and minimum, right? And the same thing is true for two variable also. So suppose you have a function from R2 to R, right? And in this case, so let me define critical point first. Okay, we will define that. And a comma b belongs to R square, right? And where f attains its local maxima or minima, then a comma b has to be a critical point. So I need to define critical point in two variable case. So what is critical point? So if of f at a comma b equals to 0, this is nothing but del f upon del x at a comma b is equals to 0, or and del f upon del y at comma a comma b is equals to 0. And the second condition, one of the any one of del f upon del x at comma a comma b and del f upon del x at comma a comma b does not exist, right? Then you can say, then you say that point is a critical point, right? So if you are looking for a local maxima or minima, then just check for critical points. You will get local maxima or minima there only, right? So now suppose you have a critical point, right? How to figure out that that point has a local maxima or minima, right? So there, for that we have some. So I'm not going to. So suppose your d is, so suppose f is your function from R2 to R, right? And a b is any point belongs to R square is a critical point, right? So suppose your d is, so calculate partial derivative fx y square minus, okay. So calculate partial derivative, double derivative fxx fyy minus fxy to the square, right? Then your case first is if your d is greater than 0, right? And your fxx is also greater than 0, then you will have local minimum at a comma b. I'm everything I'm writing for a comma b point, right? Now the second case is if d is greater than 0 and f of x comma x is less than 0, then f will have local maxima at a comma b, right? Everything is we are doing for at point a comma b, right? This partial derivative is also at point a comma b. These partial derivatives are also a comma b. Everything is calculating so at a comma b. Now case 3. Now if your b is less than 0, then a comma will be a saddle point. I will explain what is a saddle point. So a saddle point means it will not have any local maxima or local minima. That's called saddle point, right? It won't have any local maxima and minima at this point, right? Now case 4 is if your d is equals to 0, then we can't conclude anything, can't say anything. So these property you need to check for local maxima and minima, right? You can try. Suppose you have a function. Suppose you have a function f of x y is equals to 4 plus x cube plus y cube minus 3xy. Now you find critical points of this function and try to check whether this function has local maxima and minima at those points or not. You can check this point, this function. Now you can check for this function 4x minus 2y plus z is equals to, okay, this is 4x minus 2y plus z, right? So we can quickly solve one question, which, so let me, okay. In 2024, they have asked that, okay. Okay, so they have asked that suppose you have a function from R to R, right? And your function is this one, right? And they have given you that a comma b is the point of local maxima at f, right? Then what is f a comma b, right? Now if you calculate partial derivative del f upon del x, so this will be equals to 12y e to the power minus 2x plus 3 and plus, so actually it will be minus 2 into 12xy e to the power minus 2x plus 3y minus 2, right? And we need to put this part equals to 0 to calculate critical point, right? Now take this part as common, e to the power something, and 12 is common, right? Hello.
Yes, sir.
Okay. So this will be y minus 2 and this is xy, right, equals to 0. So this will give you y equals to 0 and x equals to okay, y equals to 2 and x equals to 0. Y is common. Okay. Oh, wait a second. Wait a second. So this will give you y equals to 0 and x equals to 1 by 2. Right? Take y as a common. So you will get 1 minus 2x equals to 0. So you will get y equals to 0 and x equals to 1 by 2. Right? Similarly, if you put del f upon del y, this will be equals to 12y e to the 12x e to the power minus 2x plus 3y minus 2 minus 3 into 12 xy e to the power minus this part, and from this you will get x equals to 0 and y equals to 1 by 3, and you can check that you will only attain local maxima at 1 by 2 and 1 by 3. This will be your point of local minimum, maxima. Right. Now calculate value of f at 1 by 2 and 1 by 3. So what is the value of f 1 by 2 at 1 by 3? So this will be equals to 12 into 1 by 2 into 1 by 3 e to the power minus 2 into 1 by 2 plus 3 into 1 by 3 minus 2. So this will be 0. So this will be 12 into 1 by 6 e to the power minus 0. In total, you will have 2. So answer will be your 2. And other point you can check, you won't have local maxima at those points. So other point, remaining point are 0, 1 by 2, 0, and 1 by 2, 1 by 3, and 1 by 2, 0, 0, 0. On these points, you can check you won't have local maximum. Right. So with this, let me stop here. So if you have any question, you can ask here. So if you are following me and if you have any question, feel free to ask. You can ask me here any question if you have.
सर वो थोड़ा सा लाग्रांज मल्टीप्लायर के बारे में बता देते हैं, उससे कैसे सॉल्व करते हैं क्वेश्चंस.
So Lagrange multiplier, is it in your syllabus? I don't know.
नो सर, सिलेबस में नहीं है, पर देयर आर क्वेश्चंस.
Okay. So suppose you have a f function f, right? So maybe in 2 variable or 3 variable, x, y, z, right? With some constant, right? Say z of x, y, z equals to something or 0. Right. So Lagrange what Lagrange multiplier says. So put this function is equals to lambda times g. Oh, so and this one lambda upon delta x equals to lambda times delta g upon delta x, and similarly delta f upon delta z equals to lambda z upon this. And from these conditions, find the values of lambda. Value of lambda, right? Of course you will get value. So try to find value of lambda in terms of maybe you will get x, y, z, and from this constant try to find values of x comma y, x and y and z, and then put these values in the function. You will get your answer. This is Lagrange multiplier only, right? This is your
Okay,
Lagrange
okay,
multiplier.
sir. Okay, sir.
Any other question? So if no questions, so let me stop here.
So, Dr. Akshay Kumar, sir, we are deeply grateful for your presence. We appreciate the time you took to share your knowledge with us. Thank you for your valuable contribution, sir, towards this work to this workshop. So we are honored to have you with us, and we look forward more such sessions in future with you. Thank you, sir.
Sure, sure. Thank
Yeah.
you.
So for students, please, we have shared feedback link in the chat box regarding sir's session. So please look at that, and I request you all to kindly give your valuable feedback. So next session will be on tomorrow, that is Friday, 17 January, from 6 p.m. to 8 p.m. as per the schedule. So let us meet there. Good night. Goodbye.